Thank you for showing up late in the day, and thanks to the ICT program for funding this. This is development we just started a few months ago, and we're going to continue for the next couple years. And I'm speaking on behalf of the MASPEX-ORCA team. Oops, not good. Oh, sorry, those arrows. Got it. And I just wanted to tell you what our objectives are. We're interested in searching for organic biosignatures and indicators of habitable conditions on both current and former ocean worlds. So we love Europa. I love Enceladus. We all love Titan after the glorious announcement this afternoon. But we're also interested in other places like Ceres that might tell us something about former ocean worlds processes. So we're interested in developing general capabilities to assess biosignatures and habitability. And so what do I mean by organic biosignatures? So we're very interested in some of the classical tests for biosignatures, things like the distributions of simple amino acids. This is aspartic acid. Peter Willis gave a great overview of these kinds of concepts. More complex molecules that might be only produced by biological processes, as well as carboxylic acids. You could have simple carboxylic acids that might either serve as food sources or as products of metabolism, as well as lipid-forming carboxylic acids. And you can't see this image too well, I'm sorry to say, but this is just one example of a complex type of organic material known as a humic acid. Some people think that this is a reasonable analog to the organic material that's been found in Enceladus, and we're interested in trying to characterize these types of materials on other bodies, as well as more geoprocessed products of these kinds of substances like kerogen, for example. And then when I mean habitability indicators, I'm talking about both individual molecules. So you could imagine we're very interested in, is there sources of nitrogen on Europa's surface or in the ocean that might support habitable conditions, as well as reactions. So if you want to assess, is there enough chemical energy to support life? Well, you can't just say there's hydrogen, there's energy. You actually have to consider full reactions. So for example, if you're interested in methanogenesis, you need measurements of CO2, hydrogen, and methane so you can evaluate the potential for chemical energy. Makes our jobs a little bit harder. Just to illustrate why this is useful and why you might care about this, a couple years ago we had a paper analyzing this in the Enceladus plume. We had these measurements of coexisting hydrogen, methane, and CO2. And when you have those measurements, then you can construct these types of frameworks for evaluating how much chemical energy there is in that environment. So this is known as the chemical affinity, number of kilojoules, so that's energy content, as a function of different geochemical conditions. And we identified this as the sweet spot for Enceladus' ocean. For Europa's ocean, we have no idea. So that's why we're very interested. And this just makes the point that in addition to organic molecules and biomolecules, we should also think very seriously about simpler molecules that could affect biological processes. So MASPEX-ORCA is a collaboration between 3 institutions. And so I'm just going to show you schematically what the instrument entails and what we're hoping to build. So we have a front end that's being developed by APL. I hope they still have time to do this work after winning that contract. And then we also have the University of Michigan, who's building a GC device, and I'll get into this. This is a really cool development. And then lastly, the detector is a mass spectrometer. So I'm going to mainly talk about the Swirly mass spectrometer known as MASPEX, but we also have a different option that we're investigating from the University of Bern, known as a neutral gas mass spectrometer. And so we're evaluating the trade because Swirly's MASPEX is very souped up and it's very capable, but it's more costly in terms of spacecraft resources. And then the Bern instrument is our lower resource option. So we're trying to assess the resource requirements versus the science payoff. Just to kind of set the context, I think Peter did a good job on this too. In very simple terms, I think we're going to be faced with this inconvenient truth about Europa and other ocean worlds, that they're probably going to be impure bodies hosting complex mixtures if we look at meteorites or natural waters on the surface of the Earth as a guide. So we're not going to have like one amino acid encased in ice and be able to quantify detection limits in that way. We have to figure out some way to handle complex mixtures of various substances. And how we do this just kind of shows you a flow chart of how the front end of ORCA is designed to work. So you can imagine you start with a mixture of all sorts of interesting things like salts, water, different gases, organics, refractory or light organics, And then you have to find a way to systematically simplify the mixture and analyze them. So that's what we're developing to do. So you can start with this horrible mixture. It's very interesting. You can do a first step where you melt the ice, and then you can purge the headspace. You can analyze some volatiles. That's step one. Then in the next step, you can envision, start heating this mixture up that's left over, and you can drive away the water. You can drive off some of the lighter hydrocarbons, like the gasoline-type hydrocarbons, analyze those with a GC and a mass spec. And then we're doing this other development I'll detail in the next slide. We're exploring options for how we'd analyze amino acids using things like derivatization and salt removal. And the final part of this process leverages some of the development that people have done in the past, like the SAM investigation, where you just start baking this stuff, and then you can break off different pieces of this complex organic material, and you can learn something about its chemical character, which is really useful to know. Here's the Wetlab Desalination chip. So why we think this is so useful and important is because if you have a lot of salts, which was recently rediscovered just a couple weeks ago, they can interfere with chemical derivatization reactions, which make amino acids amenable to GC analysis. So we've got to figure out a way to deal with salts. And what we're developing, and APL has been building this device, is you can imagine you start with a mixture of water, salts, and amino acids. And then they have an ion exchange resin. So when you flush this solution through there, what happens is the amino acids stick to the resin, and the salts get flushed out into the waste. And then you do a subsequent elution with ammonium hydroxide, and that can pull out the amino acids. So that's a way to do the separation. And this figure here just shows a lab demonstration of how that works. So you have a calcium chloride brine. You start flushing it through. The amino acid sticks to the resin. The calcium chloride just goes straight through. It's perfectly happy. And then you do the ammonium hydroxide wash, and then you see tryptophan. I think this is one of the really cool things. I'm willing to risk my neck that this could be the future of GC for spaceflight missions. So you might have dealt with GC in the laboratory, and it's like these horrible metal coils and cages, and it's wrapped around there, and it takes a lot of space, and it's difficult to handle. Well, what we're developing is a micro device GC. So you can see here, these are dimensions. It's on the order of centimeters or inches. And the column is actually etched on a silicon chip right there. So this is a column that's actually 10 meters long, but it doesn't take up 10 meters of space. It's actually really small and nice to use. And so what you actually do is you pump in a sample that goes through a pre-concentrator, so you get a nice plug of organics, and then you thermally desorb it through this column, and then you can do analysis. So we have one option where you could do an alternative analysis with a micro photoionization detector, or we could also just go directly into the mass spec. In our lab model, we just plug in a USB drive directly into a data acquisition board, and we start getting some data. Here's some data we've collected with the IC2 investigation. So this is just a really simple mixture to demonstrate the proof of concept. So we just did a quick isothermal and then some temperature ramping shown here. And then in a span of like 2 minutes, you're able to separate these simple hydrocarbons from pentane to nonane pretty effectively with this small device. So we're feeling pretty optimistic that this might have some promise. What's to come? So the really cool thing is you could actually then add additional columns on the same silicon chip. So you have the first GC column, like we all know, and that gives you all these peaks. And you can add a second column after that, and it adds greater ability to separate because you can use different types of stationary phases. So the first stage, you could use like a non-polar column. Then here you could use a polar column, and you can pick different chiral columns. So there's a lot of flexibility for tuning this to different types of analytes. So we're really excited about that. And here's some demonstration of what our Michigan team had done previously, where they just took a mixture of 50 volatile organic compounds. And you can see, so instead of having peaks, you actually get these little spots in 2 dimensions. And what's nice about it is some of these spots are the same horizontal distance away. So if you had a one-dimensional chromatogram, they would fall on top of each other and not be separated. But if you have the second dimension, then you can actually pull them away from each other and do a nice, clean quantitative analysis. Here's MASPEX. I love MASPEX. MASPEX is being developed for Europa Clipper, so it's leveraging that heritage. What we're really hoping to do is provide the local scale information to complement what Clipper is going to tell us from the global perspective using the same instrument. So it's a nice way to compare and contrast that. Mass specs can go up to 1,000 atomic mass units, so it has a lot of flexibility for looking at small things or big things. It can go up to 50,000 resolution M to delta M, so you can pull apart a lot of things that are very similar in mass. And what we're hoping for this to be is a pathfinder for isotope biogeochemistry on the surface of icy worlds. And I'll kind of show you how this works. So this is a famous plot in geochemistry showing how you can organize the origin of methane based on carbon and hydrogen isotopes. And there seems to be certain regimes that separate abiotic versus biotic gases. So we're trying to use these kinds of empirical rules and rules based on physical chemistry, and then trying to compare that to the data on Europa, which we don't yet have. So I think this is a nice path forward for this type of isotope work. Why you need high resolution. So the classic case that we've struggled with Cassini is separating things like CO from N2. They have a nominal mass of 28, so Cassini, we're stuck. We have big problems there. But with mass specs, you can see in this lab demonstration, we're nicely able to pull apart those peaks and to discriminate between CO and N2. And this is really important, so if you want to fill in that methane isotope plot, well, you need to measure both 13C methane and deuterated methane. Those both have a mass of 17, so that's a problem unless you have high resolution. And if you have high resolution, it's great because these species actually differ at some of the decimal place level of mass. So we like to think of decimal places as our friend for mass specs. And I mentioned organics are of great interest too. So here's some data we've generated from IC2 so far. So this is a standard mixture called Grove mixture. Contains a suite of nonpolar or weakly polar organics. So the examples I'm showing here are 1-octanol and decane. This is what the manufacturer sends to us. This is the mass specs data. So we're able to reproduce with similar efficiency what you can do in the conventional laboratory. Here's what the mass spectra look like. So these are from NIST, these little stick figures, and MASPEX is able to produce comparable stick figures over a wide range of mass. And we've just started working on some quantitative analysis. This just shows some of these calibration curves we've generated as a function of concentration and then the peak areas that I showed in the previous slide. So it's looking pretty promising, but we'd like to improve this in the next year or so by starting to use internal standards based on fluorinated compounds, for instance, and then extending these to even lower concentrations, which some people might expect for the surface of Europa. And with that, I will open up for any questions. Thanks.
Any questions for Chris? Yeah, come use the mic quickly.
So the column on the silicone chip is really cool. It's very innovative and neat. But even looking at low masses, one of the big things that makes a GC heavy and big is the oven part, right? And you need it for bakeouts to make sure you keep your column clean. So then what's the temperature, what's the high temperature you can get to with the chip column?
The high temperature, I think, is around 350 degrees Celsius. Yeah.
Cool, that's great.
Anything else? Go for it.
Hi. So do you guys have you been able to measure any changes in flow rate along this kind of more circuitous path?
I don't, well, maybe the University of Michigan team has, but we haven't had that test with mass specs yet. So what we're hoping to do with IC2 is we want to interface them together and then test for these various organic mixtures. So we'll have those data hopefully next year at this time. Great, thank you.